Hello and welcome back to Basic Topology, the video series where we talk about topological spaces and their applications. And indeed, in today's part 6, we will look at a very important kind of topological space, namely a Hausdorff space. And soon we will see that such a Hausdorff space still carries a lot of properties we know from metric spaces. However, before we go into the details, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, as a Steady supporter you can access a lot of additional material like PDF versions, books and quizzes. And by clicking the link in the description, you can see that the annual membership is not so expensive. Okay, then without further ado, let's immediately start by looking at the topological space Xt. So X is a set and T a collection of subsets of X. And as you already know, these special sets we call open sets. So the topology of T tells us which subsets of X are open and which are not. Hence, depending on the topological space, we could have a lot of open sets or only a few. And this is a crucial thing if you want to separate two different points X and Y in our space. Because it's simply not guaranteed that you can find two disjoint open sets, one that contains X and one that contains Y. Only if we can do that, we would say that we can separate the 2 points. And as you might know, this is always possible in metric spaces because we have our epsilon balls. However, in a general topological space, this might not work, and we already know one example where it fails, namely the indiscrete topology. There, the only open sets are given by the whole space X and the empty set, which means we cannot separate two different points. And now you might already guess, whenever we have this property given, our topological space is called a Hausdorff space. However, before we formally define that, I first want to talk about neighborhoods. This is quite a helpful definition when we fix a point in a topological space and we want to talk about the subsets around this point. Therefore, now let's fix a point X in X. And now most importantly, we don't restrict ourselves to open sets, we can take any subset A that contains the point X. So we have a lot of choices and some of these subsets are called neighborhoods of the point X. Indeed, the name already suggests that a lot of points have to lie around X. And in the topological space, this would mean that we can find an open set that contains X. And moreover, this open set that we can call U has to lie completely inside A. So you could say we have to find a small enough open set. This means it should be a subset of A, but it still should contain X. Hence, obviously by this definition, this open set U is also a neighborhood of X. But for sure, the advantage of this definition is that any bigger set can also act as a neighborhood of the point X. And to see this definition in action, let's immediately look at an example. And before we get too crazy, let's first look at the real number line with the standard topology. And there, if you fix a point X in R, we can look at a neighborhood of this point. So for example, if you take the interval from X to X plus 1, then it should be obvious that this is not a neighborhood of the point X. It's simply not possible to find an open set that contains X and lies completely in this interval. On the other hand, if we take the interval from X minus 1 to X plus 1, then this one is a neighborhood of X because we can immediately state an open set U. For example, we can just take the open interval from X minus 1 to X plus 1. In fact, this is already small enough because it lies completely in our closed interval here. And this might be already good enough for examples because I think the notion is quite clear. And indeed, we can immediately use it for the definition of a so-called Hausdorff space. So as always, we just take a topological space Xt and now we call it a Hausdorff space if we can always separate points with neighborhoods. So more precisely, for any 2 points X and Y, which are not the same, we can find two neighborhoods which we could call A and B. There A should be the neighborhood of X and B the neighborhood of Y. And now what we want is that we can choose these neighborhoods in such a way that they don't overlap. In other words, the intersection of A and B should be equal to the empty set. So it's exactly the same picture from the beginning. With neighborhoods we can separate the 2 points. And there you might already know that such a property is needed if we want to talk about unique limits of convergent sequences. In fact, we didn't define convergence in a general topological space yet, but that's something we will do soon. But first, let's write down the typical example of such a Hausdorff space. Namely, this is just a general metric space. This includes already a lot of examples, for example also R with the standard topology. And here in the first step we can say that we forget about the concrete metric and just consider the open sets. And that means what we get back is a topological space. And now it's not hard to show that this topological space is always a Hausdorff space. This is quite easy to see because you can take 2 different points x and y in the metric space. Hence the measured distance between the 2 points has to be greater than 0. And perhaps let's call this distance r, which gives us a positive real number. Therefore, separating these 2 points with distance r should not be too complicated. There are a lot of possibilities, but maybe just let's split the distance in 3 parts. So we can define epsilon as r divided by 3. And with that we immediately have our neighborhoods by the epsilon balls around the points. Which means both neighborhoods we consider here have the radius epsilon. And then one is centered at x and the other one at y. And now by construction they cannot have any points in common because otherwise the triangle inequality would not be satisfied. And with that we have shown the Hausdorff property. So you can already keep that in mind. A Hausdorff space is a generalization of a metric space. And soon we will look at Hausdorff spaces which cannot be induced by a metric space. In that sense, this is definitely something new, something that is more general. But even for metric spaces, it's often helpful to just work in a topological manner where we can use the Hausdorff property. But this is definitely something for the next videos, so I really hope I meet you there again, and have a nice day. Bye bye.